Okay, it's time to discuss chapter 3 of our course, and this chapter is on ionic compounds. Remember, we defined a compound as a substance that is made of two different elements. Example, sodium chloride. Example, H2O. Two different elements in them. Hydrogen, oxygen in water, sodium, chlorine in sodium chloride. And since we are talking ionic, I'll narrow down to substances like sodium chloride, which are made of a metal, which is a sodium, and a non-metal, which is a chloride. So let's discuss how these compounds are made and their characteristics. The learning objectives. The learning objectives of chapter 3 on ionic compounds is simple. We will describe the basic features of ionic and covalent compounds. We'll use the periodic table to determine whether an atom forms a cation or an anion. Cation will be positively charged species, anions negatively charged species, and we will determine its charge using its group number in the periodic table. We'll describe the octet rule, where most of the elements in the periodic table should have 8 electrons around them. We'll write the formula of an ionic compound, bearing in mind they are made from combination of metal and non-metals. We will use IUPAC system of naming to name ionic compounds and describe the properties of these ionic compounds, their solubility, conductivity, how they form electrolytes. We'll recognize the structure of the most common polyatomic ions and name the compounds that contain the polyatomic ions. Poly means many atom ions, polyatomic ions. For example, OH minus, SO4 2 minus, CO3 2 minus. They are polyatomic. They are made of different elements, but again, they are charged. So they are ions, polyatomic ions. We'll discuss those and the naming of the compounds composed of them. And then we will list useful consumer products in real life and drugs that are composed of ionic compounds. Let's dig in. What is bonding? Bonding in chemistry is the joining of two atoms in a stable arrangement. And I'll have you know ahead of time, in chemistry, a single bond, any individual bond, is made of two electrons. So anytime you have two electrons between two elements, we say you have a bond. The bond is made by orbital overlap. In bonding, elements will gain, lose, or share electrons to reach an electronic configuration of the noble gas closest to them in the periodic table. We'll talk about that. So a chemical reactions happens where there's gaining of electrons, there's losing of electrons, or the sharing of electrons. A chemical reaction will happen at that. When this happens at that event, there are two different kinds of bonding. There is the ionic bonding, which result from the add complete transfer of electrons from one element to another. Remember, sodium has one valent electron. Chlorine, on the other hand, chlorine has 7 valent electrons. Is in main group 7. I'm just showing the outermost electrons in the outermost shell. We've covered this. So when this electron is given to chlorine, because it's more electron wanting, we say he's more electronegative. The sodium will be 1 electron less. We put a plus charge. The chlorine will have 1 electron more. We'll put a negative charge. The other electrons are still there. So we are showing the red electron right here that was added, and this is a product made of metal and non-metal. So between them, between sodium plus cation and Cl minus anion, right between them, we'll say we have an ionic bond. Why? Because there was complete electron transfer, as I've shown with this fishhook arrow right here. The metal donates or loses the electron, the non-metal, the chlorine gains it, and that's when we say we are making ionic bond, always between metal reacting with non-metal, as explained here, how to make table salt sodium chloride. Covalent bond, on the other hand, results from sharing of electron. They could be equal sharing, or it's just one element giving all the electrons. Suppose you have a hydrogen atom with one valent electron. We know it has one valent, and another hydrogen one valent electron. When these guys share, what we will get is hydrogen gas. So I told you that a bond is made of two electrons, so you'll get hydrogen gas. So you see that there was sharing, and if there was sharing, the bond between HH, this bond is called covalent bond. So that is a quick overview, but we can discuss more on this. Introduction to bonding, part 2. Ionic bonds, they form, like I said, between a metal and a non-metal. Usually the metals are found on the left side of the periodic table. So remember the structure of the periodic table. With the exception of hydrogen right here, you will have the metals all somewhere here, including the lanthanides and actinides, the two rows that are usually down below the periodic table. Okay. The nonmetals, on the other hand, they are found mostly on the right side of the periodic table. Okay, the nonmetals are found mostly on the right side of the periodic table, including the chlorine there, while the metal sodium will be somewhere here. Okay, so now you are looking at a sample of sodium metal. This is a sample right here of sodium metal, and it can really be scrapped and cut out. It is a metal. You expect when you cut it, it's going to be shiny, just like aluminum. And then you are looking at chlorine. On the next flask, you are looking at chlorine gas. I told you the halogens are diatomic. They don't exist just as Cl. They usually show up in pairs, like Cl2, Br2, and they're usually gases. So that is a gas, chlorine gas. The metal is monoatomic, okay, and it can be in ionic form. We just talked about it. The metal is monoatomic, the non-metal is diatomic. When these two combine, when Na and Cl2 combine, I told you, will result in formation of a cation of sodium by electron transfer from sodium to chlorine, and an ion of chloride. Okay, an ion is just negatively charged species, cation is positively charged species, and I explained to you how the ionic bond is being made right here. Now let us introduce the covalent bonds, then we can look at some examples. Covalent. When you see the prefix co, that means there's a association, like colleague, two individuals doing something together. So covalent bonds are formed when two nonmetals combine, and they combine by sharing. When there's sharing of electrons between nonmetal and nonmetal, you're most likely having a covalent bond. I gave you the example of hydrogen and hydrogen. Those two are nonmetals. They give you hydrogen gas. Okay. A molecule is a compound or element containing two or more atoms joined together with covalent bonds. And again, hydrogen gas is an example of that. H2O is an example of that because the H2O itself has nonmetals. Hydrogen is nonmetal, oxygen is nonmetal, hydrogen is nonmetal. The bond between them must be made by sharing of electrons, and it's covalent. Covalent bonds and molecules will be discussed in more detail in the next chapter 4. Now here you're looking at an example I showed you before of hydrogen. Remember that hydrogen has atomic number Z equals to 1, meaning that it has one proton that is neutralized by one electron. So if you are to write the electronic configuration of hydrogen, it's just 1s1, one valent electron, which are these two dots. So when you use fishhook arrows to show one electron movement combination of the electrons, they join up to come in between those two elements. The two electrons are shared and they form what we call a covalent bond, which is that's the covalent bond formed by sharing. The same would happen if we were sharing between two chlorines. So chlorine is in main group 7. I'm only showing the dot symbol of the elements and I'm putting those electrons together. When that happens, you're going to get Cl with now 6 dots and Cl with another 6 dots. The bond in between there is also covalent bond because they're sharing. That gives you chlorine gas, by the way, and so many other examples. So now let's get back. We gave the introduction of ions. We've given the introduction of covalent structures and covalent bonds. Now we can give details of each of these. We start with ionic compounds and how ions are formed. What are cations? What are anions? Ions are generally charged species in which the number of protons and electrons in the atom are not matching. They are unequal. Okay? And if you have a charged particle that is positively charged, we call it cation. If it's negatively charged, we call it anion, not onion. Ionic compounds, we say they are usually made of a metal and a nonmetal, and they consist of oppositely charged ions that have a strong electrostatic attraction of each other. I will give you an example here. So let's go back to point 1. Ions are charged species in which the number of protons and electrons in the atom are unequal. Now, if you have sodium with one valent electron, that's why it's in main group 1, it's gonna lose that electron. Okay, ionization energy, we talked about it, the energy required to lose and to remove an electron. It will lose it to give you Na plus and the electron that was lost. So the Na plus here is a positively charged species, is an ion. Ions are characterized by presence of charges, but which ion? Because of the positive charge, we call this cation. Now, on the other hand, the chlorine only needs one more electron to have 8, which is the octet rule. So for chlorine, he will gain an electron that was lost by the sodium to give you a chloride with 8 electrons. Now there's an extra valent electron. Because the chloride has a negative charge, it's called an ion. It's an ion. But what type of an ion do we have? The anion will be the name. The name anion will be given to the negatively charged species. Now I say that Na plus and Cl minus, those ones are what give us the table salt, and this is ionic compound, which is chapter 3. Now let's qualify this. The number of protons and electrons are unequal. So remember, when you're losing or gaining electrons, the number of protons don't change. It's chlorine 17 with the 7 valent electrons. It's still chlorine 17 with the 8 valent electrons. So number of protons is 17 regardless. However, number of electrons, here you have 17 electrons. Here, because you gained, you have 18 electrons. So you see, ions are charged species in which the number of protons and electrons are not same. You can do the same thing for sodium. So sodium with 1 valent electron has 11 protons. Sodium which has lost the 1 valent electron, now it's a cation, still has 11 protons. Before losing the electron, this sodium, neutral sodium, will have 11 electrons. After losing the 1 electron to, say, chlorine, the electrons will go to 10. So again, you see that the ion of sodium has different number of protons and electrons. So I've explained point 1. Point 2, ionic compounds consist of positively charged ions that have a strong electrostatic attraction of each other. Correct. Na plus, Cl minus will have a very strong electrostatic attraction of each other. And they attract to give you a crystal of sodium chloride, what we call table salt in the real world. So like I said, the positively charged ion is cation, the negative charged ion is anion. Okay, more on cations and anions. Remember, we said cations are positive ions, anions are negative ions. Example of cation was Na plus, example of anion Cl minus. Okay, you will see that cations are positively charged, and a cation will have fewer electrons because they lose electrons. They have fewer electrons than protons. I explained to you that before losing an electron, the valent electron, these 3s1, a valent electron from the valent shell, the sodium has 11 protons. The atomic number Z is 11. Now, after losing the 1 electron, so let's say plus electron lost, the sodium will have a plus charge because it lost 1 negative, and he still has 11 protons. Okay, so still Z will be 11 protons, but the number of electrons decreased by 1. We started off with 11 electrons, we're left with 10. It decreased by 1, so it's 10 electrons. So yeah, we expect that cations will have fewer electrons than protons, but it will be the opposite for anions. Anions will have more electrons than protons, which is why they will be negatively charged. They have more negatives than more positives for anions. For cations, cations will have more positives than the negatives, the electrons. Now, our electronic configuration was 1s2, 2s2, 2p6, and 3s1, the valent electron, which is why I'm just showing the 1 dot. When this is lost, all you're left with is 1s2, 2s2, 2p6, and that is the same electronic configuration as the noble gas neon, which is why we said to form ions, the reaction will happen in a way that the ion formed will have the same electronic configuration as one of the noble gases. All elements react to gain the noble gas electronic configuration, which is very stable. That is the idea here. So here, sodium is reacting, so it can lose the unfilled third shell. Then it will be left with all filled, the first and second shell, to give you neon, which also has 10 electrons, just like the Na plus. And the term used when you have similar elements having the same electronic configuration, we say that those species are isoelectronic. So sodium and neon are isoelectronic. They have the same number of electrons, hence they have the same electronic configuration. That is formation of the cation. That's formation of the cation Na+. You've seen me do this several times now. Okay. Now you can do the same thing for magnesium as an example. Magnesium is in main group 2. It's right here, main group 2. You see the blue box I clicked. Magnesium is in main group 2 with atomic number Z equals to 12. So he has 12 protons. Atomic number is 12. If he has 12 protons, I expect him by inference to have 12 electrons around the nucleus. So we should have somewhat 12 electrons around the nucleus. Okay, I'm not putting all the count of 12 dots, but I'm just showing you the shaded blue area is the electron cloud. So you have 12 electrons before reacting. Now, if you look at the periodic table, magnesium has so many steps to go to argon. But if he can go back 2 steps to sodium, then jump up to neon, neon will be the closest noble gas. Neon is the closest noble gas to magnesium. So magnesium will react by going back, by losing 2 electrons. Okay, going back to neon. So in that case, he reacts by losing 2 electrons because he has 2 hopes going backwards to neon upstairs. So let's write 2 electrons here lost. When the 12 electrons lose 2 of them, you are left with 10 electrons, which are these after the loss of the 2 electrons, and that is similar to the 10 electrons in neon. So again, once you lose the 2 electrons from Mg, you're going to get Mg2 plus, and the 2 electrons that are lost, this one here will have 10 electrons because it started off with 12 electrons. The 10 electrons are similar to that of neon, so the noble gas electronic configuration is just neon. Again, elements react in such a way to have the same number of electrons as one of the noble gases which are stable. So this is the electronic configuration now of Mg2 plus, and it so happens to be the same electronic configuration of neon. So Mg2 plus will have this noble gas electronic configuration. So we can say again now Mg2 plus, Na plus, and neon have the same electronic configuration, so they are isoelectronic. Okay. Did the number of protons change? No. Number of protons stayed 12 as before. Did the number of neutrons change? No. The only thing that changed was the number of electrons from 12 to 10. Okay, absence of electrons lost equals to presence of positive charge. So you lost 2 electrons, Mg becomes Mg2 plus cation. Let us talk about anions a little bit. We just said that metals react by losing electrons. The nonmetals themselves, they're going to react by gaining the electrons lost by the metals. When someone loses, there must be someone who is gaining. It's always like that. So anions are negatively charged ions because they tend to have more electrons than protons. An anion has more electrons than protons. Now let's take the case study of chlorine. Chlorine is having atomic number 17. So Z is equals to 17, meaning he has 17 protons. What we have here. He usually has 18 neutrons to give us a mass number of 35. About 35.45. So if we have 17 protons in the neutral atom of chlorine before he reacts, we by inference say that we have 17 electrons, which is the blue electron cloud you see right there. If you write the electronic configuration of chlorine, it will be as written: 1s2, 2s2, 2p6, 3s2, 3p5. Now focus on the valence, which means outermost shell, and the valence electrons. So this one has 7 valence electrons. Now usually we want to fill up orbitals to get the octet state. So if we are at 7, how many more electrons do we need to get to 8, which is the octet state? Only 1. So now you have 2 options: either entirely lose the third shell, meaning lose 7 electrons, or gain just 1 to be octet. Which is easier? Of course, gaining is easier. Gaining is easier. You just gain the 1 instead of losing the 7 to have fully filled orbitals, which is what chlorine will do. So our chlorine, which has 7 valence electrons, like I showed down here, would rather gain 1 more. So now he'll have octet state out there with 8 electrons, which is considered stable state. Because now he has 8, he has 1 foreign electron. Pretend that this was the foreign electron that was added. A dot is representing the electron. You're going to get a negative charge, that extra 1 electron. Okay, so now we started off with 17 electrons, and now chlorine has gained 1 to be 18 electrons, and it's no longer chlorine, it's called chloride. He's negatively charged. It's not a cation, it is now an anion. Anions are negatively charged species. So that is the idea. You can tell that the number of protons and neutrons did not change at all. We started 17p, 18n. We still have 17p, 18 neutrons. The only thing that changed was the number of electrons. Now we have 17 protons versus 18 electrons. So it's true to say that really anions will always have more electrons than protons. Anions have more negative charges than positive charges, the protons. Anions have more electrons than protons. Now in this part, let us relate group number to ionic charge for the main group elements. Remember, in the periodic table, the main group elements were the tallest column of the periodic table, which are found on the left and on the right, ignoring the transition metal elements that are right there in the shaded, black shaded area. So those are the main group elements, and they're usually, I think, 8 columns. Can't split this enough, but they're usually 8 columns of the periodic table. So to remind you, metals will always form positively charged species we call cations. For the metals in group 1a, that is alkali metal, group 2a, that's alkali earth metals, and group 3a, the group number is going to be equal to the charge of its cations because it's equal to the number of valence electrons that tend to be lost. In group 1, the valency is 1. Example, sodium. I'll keep using sodium. You have 1s2, 2s2, 2p6, 3s1. 1 valent electron in the outermost third shell. So sodium is found in the third period and is found in group 1 because it has 1 valent electron and it's right here. So we can write Na dot. We expect it's easier for him to lose the 1 electron than gain 7 more to be octet. And then you'll be left with the second shell filled up with 8 electrons. First shell is filled up with 2 electrons. Happy, happy. So when 1 electron is lost from sodium, it gets a plus charge, the electron is lost. So we are saying that we have plus 1, and therefore sodium is expected to be somewhere here in group 1. Okay, and you'll see in the periodic table sodium is right there in main group 1, matches the plus charge 1, the plus 1 that he has once it loses the electron. Group 2, we can use the example of magnesium. Magnesium has a valency of 2. Remember, magnesium has 12 protons, so it has 12 electrons, and we can write the electronic configuration of as 1s2, 2s2, 2p6, 3s2. These are filled up. They are called core electrons or core shells. These are the valence. It's easier for us to lose the 2 electrons than gain 6 more to be octet. So example here is magnesium is gonna get Mg2 plus. I come here, I say Mg2 plus, and we lost 2 electrons. Notice that we have a 2 plus. So again, then the group number will be equal to the charge of cation. You'll see magnesium in main group 2 or column 2 in the periodic table. He's right there next to sodium on the second group, alkali earth metal. Okay, magnesium is right there. Main group 3, I'll give you the example of aluminum with 13 protons, which means it's gonna have 13 electrons, which is 1s2, 2s2, 2p6, first and second shell filled up, that is the core, then 3s2, and then 3p1. So we can already see that we have these electrons here in the valence shell, and the valency is 3 electrons. So he reacts by losing 3 electrons. It's easier for the third shell to lose the 3 electrons than gain 5 more to be octet. Okay, so this is gonna cross out. So aluminum with 3 dots would rather give you Al3 plus, as it loses the 3 electrons as shown in the general reaction here for group 3 elements. Now notice that aluminum is Al3 plus. You'll see aluminum right here. Overall group 13, the longest column is going to be the third one, skipping the transition metal elements, so main group 3A. So it's true, the group number will usually match the charge on the cation for group 1A, 2A, and 3A. Now, what about the anions? How does the charge on anions relate to the main group elements? Talking about group 1A up to 7A. Anions will be starting from 5A, going to 6A and 7A. Let us look how their anionic charge relates to where these elements are found in the periodic table, the groups. So we know that nonmetals form anions by gaining electrons. For nonmetals in group 5A, 6A, and 7A, the anion charge equals to 8 minus the group number. The anion charge is going to be equal to 8 minus the group number. So let me give you a quick example here. Probably let me draw it like this. I'm not gonna be perfect in my drawing, but I just want you to get the idea. So I'm going to use the case of nitrogen. So I think I have, okay, one more. I think I have carbon, nitrogen, oxygen, fluorine. This is 5A, this is 6A, this is 7A. So focus on the nitrogen. Right out here we have neon. Question to you is, how many steps do we have to go from group 8A to 5A? So like saying from the neon to nitrogen, how many steps? Let's go with green. 1, 2, 3 steps. See that? So I can tell myself that nitrogen by default should be N3 minus because we went 3 steps from the noble gas. Now do the same thing for oxygen. Let me use a different color. Let me use purple. We're going 2 steps to the oxygen. So oxygen right here should have O2 minus for the anion. Let me use the fluorine and use a different color, maybe this pink one. Fluorine is just 1 step from the noble gas. So fluorine should be F minus. So you see that, which is why we are saying 8 minus the group number. So for nitrogen, it is in group 5, main group 5, right here. Neon is in main group 8. So if you do 8 minus 5, you get 3. So since it's a nonmetal, the charge on nitrogen will be negative because nonmetals make anions. Now if you look at oxygen, oxygen is in main group 6. Oxygen is in main group 6. The neon is in main group 8. If you subtract, you get 2. Again, since it's a nonmetal, that's going to be negative 2. Look at fluorine. Fluorine is in main group 7. So fluorine is main group 7. Neon is in main group 8. Okay, subtract, you're going to get 1. Fluorine is a nonmetal, so it becomes an anion. And the name of that will be fluoride. This is fluoride, this is oxide, and this nitrogen will form a nitride. So that is the idea. So you expect that every element in main group 5, like nitrogen, phosphorus should be right below the nitrogen, should have negative 3. So phosphorus will be 3 minus, nitrogen will be 3 minus. And then for group 6, oxygen will be 2 minus, sulfur 2 gives you a sulfide. Oxygen is oxide, sulfur sulfide, Se2 minus. And then the main group 7, the halogens. The halogens, they're just 1 step to the noble gases, so you get fluoride, chloride, bromide, iodide. Now since these are nonmetals, we can also explain using the chemical reaction. Let me change the color to purple. So if you're in group 5, the valence electron is going to be 5. You remember something like nitrogen. Remember an element like nitrogen with atomic number 7, it's going to give you 7 electrons with electronic configuration 1s2, 2s2, 2p3. So that means that the second shell is not filled up. The second shell is not filled up. Total valence electrons in the unfilled second shell is 5. 2 plus 3 is 5. So you get 5. And then you also get these 5 dots, the valence electrons. So is it easier to lose the 5 or gain 3 more to be 8, which is octet-true? You'd rather gain the 3 than lose 5. So it's an nonmetal. He reacts by gaining. So we put plus. That's a symbol for gaining. Plus 3 electrons. So the 5 now becomes 8 in here. Since you have 3 added electrons, the charge will be 3 minus. And that's the same thing for phosphorus. It will have 5 dots, gain 3 to give you 8 dots, 3 extra electrons. Oxygen. Oxygen has atomic number 8. So 8 electrons, 1s2, 2s2, 2p4. This second shell is not filled with 8 electrons. We have 6 valence electrons, so it's found in main group 6. Would you rather lose the 6 electrons and entirely scrap off the second shell, or gain just 2? You just gain 2. So we start with the 6 dots, the valence electrons only shown. You gain 2 more. We use the plus sign to gain 2 more electrons. So now it has 8 valence electrons. We have 2 extra foreign electrons, so it's 2 minus. So we get the oxide. It's the same process for sulfide. Fluorine has atomic number 9. So 1s2, 2s2, 2p6, 2p5. We have to account for 9 electrons. That matches the 9 protons. So again, the second shell is not filled up with 8. He has 7 electrons, so we show the 7 dots. Would you rather lose the 7 or gain one more to be like neon, isoelectronic to neon? We would rather just gain one, so we are adding 1 to give you 8 valence electrons. There's 1 extra electron, so -1. So all this will behave the same way. Okay, now let us summarize what we've learned in the last slide. We are going to summarize the relationship between the ionic charge and where these elements are found in the periodic table. So we said in summary, whenever you have group 1a element, it most likely has a valency of 1. It loses the 1 electron because group 1a elements are metals to get m plus 1. That's why elements like sodium will form n plus 1 and they're found in group 1. Same thing, main group 2 elements including magnesium, which forms a charge of 2 plus. He loses 2 electrons because he has a valency of 2 and is found in main group 2 for that reason of the periodic table. Main group 3 elements, example aluminum, he loses 3 electrons, and using the charge you can tell since he has a 3 plus, he should be found in main group 3. It's a metal. It loses the valence 3 electrons. Metals react by losing valence electrons. Now one thing I can tell you also is these elements are reacting to lose those electrons so that they will have a noble gas electronic configuration. So these three will all want to form neon electronic noble gas configuration. The three I've given, sometimes you get one with argon or even helium. For example, if lithium with 1 valence electron loses the valence electron to give you Li plus, an electron is lost. Lithium has 3 proton, meaning he has 3 electrons. If he loses 1 electron, you get 2 electrons, and that is the same as that of helium. So the noble gas electronic configuration of lithium in main group 1a will be helium in brackets. Now, if you look at the nonmetals, we know that they react by gaining, like starting from group 5a. Group 5a, you're going to find nitrogen, you're going to find phosphorus in there. After nitrogen, you have oxygen, fluorine, and then I believe you're going to get neon. Okay, after phosphorus, you're going to get sulfur, chlorine, then you're going to get argon. This is group 8a. Now, our notes reminded us that we just subtract. So if nitrogen is group 5, we'll subtract 5 from 8, we get 3. And because nonmetals react by losing, we include a negative charge. So it's gonna be, for nitrogen, it's gonna be 3n superscript 3 minus. Phosphorus will be the same thing, p superscript 3 minus. That's a phosphide and a nitride. You can look at it this way. How many steps are we going back from neon to nitrogen? 1, 2, 3 steps. We are going backwards 3 steps, so minus 3. So nitrogen, for nitrogen to go to neon, you need to go 3 steps. Okay. So 3 electrons must be gained for nitrogen to be stable as the noble gas, next noble gas to itself, which is neon. And 3 electrons must be gained for phosphorus to be as stable as argon. So it's 3 minus, and that's what happens with elements with the valency of 5, which includes nitrogen and phosphorus. Now, when you get to group 6, that's where you get oxygen. As I mentioned earlier, you can just count back. From neon, you go 1, 2 steps backwards. So oxygen will give you O2 minus. We call that an oxide. And he gains 2 electrons to get to neon. So we know that oxygen is in main group 6 with a valency of 6 because he has 2 steps to get to 8, which is the main group 8, like neon. Same thing applies with sulfur, which gives you an oxide as a sulfide. Same thing with sulfur that gives you S2 minus to form sulfide. Sulfur is here, argon is here. Sulfur has atomic number 16, argon has 18 electrons, 18 protons. Chlorine should be in the middle. So you're going 2 steps to argon, you have to gain 2 electrons. And because there's gaining, the charge will be negative. So 2 electrons means you are 2 steps to the 8. So that means you are at position 6. That means you are at main group 6. Group 7 elements, otherwise called halogens. Those ones, they are 1 step to their noble gas relationships. So if you look at fluorine, he is 1 step to get to neon. Fluorine has atomic number 9. Okay. Neon has atomic number 10, and he has 10 electrons. So fluorine will need to gain 1 electron. So it's going to give you an ion X minus, fluoride. Same thing with chlorine. Going to argon, he needs 1 step, or he needs to gain 1 electron. 1 electron gained, and it gives you a chloride. So that is the idea. Since you're 1 step to 8, these halogens must be in group 7. So it's true, the charges, the value of the charges can tell us where these elements are. In summary, we are looking at the periodic table with the elements having their ions shown with their charges. So you see, if you're in group 1, as shown here, all these will be +1. Why positive? Because these are metals. Metals react by losing. Lithium will lose 1 electron to be isoelectronic to helium. Sodium loses 1 electron to go upstairs to have the same electrons as neon. The noble gas for Na plus will be that. The lithium will be that. Helium brackets. Potassium, which has atomic number 19, will lose 1 electron to be 18 to be similar to that of argon that is upstairs. That will be the noble gas electronic configuration of K+, and so on and so on. So now, if you are in group 2, you would expect that these metals will react by losing 2 electrons. Beryllium himself has atomic number 4, so 4 protons, 4 electrons, and he will want to go back 2 steps. 1, 2, 2 back to the helium. The helium is upstairs. He's right. Helium is right there. That's where the arrow will end up, where I said 1, 2. You get to the helium. So he loses 2 electrons to give you Be2 plus. If he had 4 initially and lost 2 electrons, he's left 2 electrons. That is the same as that of helium, which has atomic number of 2, 2 protons, 2 electrons. Noble gas electronic configuration of beryllium, 2 plus cation. Cations are positively charged ions, will be brackets of helium. Magnesium has atomic number 12. He loses 2 electrons to give you Mg2 plus with 10 electrons. That is similar to that of neon. So, which is why we said before that Na plus, Mg2 plus, and neon are isoelectronic. They all have the same noble gas configuration of neon. Calcium is in main group 2. He will be 2 plus when he forms an cations. Same with strontium, same with barium. Here in main group 3, aluminum with atomic number 13 is going to have 13 electrons. Here is 3 steps. One step gets to this place, and then second step to sodium. The third step, he will get him to neon, which is right above him. So even Al3 plus is isoelectronic to the rest. He will have the same noble gas electronic configuration when he forms Al3 plus after aluminum loses the 3 electrons. And so the 3 plus charges puts aluminum right there in main group 3. Now when you come to main group 5, it's 3, nitrogen is 3 steps to the neon. He has to gain the 3 electrons. Each electron is negative, so 3 minus, same will apply with phosphorus. That is 3 steps to the argon. Oxygen and selenium, they are 2 steps to their noble gases. They have to gain 2 electrons, so they have 2 minuses. So you see how the charges balance. Bromine is 1 step to the noble gas, so he has to gain 1 to be as stable as the noble gas next door. So that is the idea. Now, if you just focus on the transition metal elements, they might have several of the charges. And these usually, we just memorize their charges when you're working with them. Some have multiple charges, so you can't really use that method to predict their superscript charges. They're just memorized usually. Here we are showing you the common ions in the human body, where they are found and what they do. So the first one, calcium, is generally found in bones, including your teeth. So that's about the group 2A cation calcium ions. Let's go down. Here we have group 1A cations, that is Na plus and K plus. They are found in all body fluids. You've heard of people talking about, I have electrolyte imbalance in my blood or in my fluids. The electrolyte imbalance is usually a corrupted ratio of the sodium and potassium ions in fluids of a human. Then you have Fe2 plus, which gives our hemoglobin the red color, especially when he is in Fe3 plus oxidized form. We get the red color catalyzed by the Fe3 plus and some conjugation processes that you learn in organic chemistry and biology. So just know cations of Fe, which is ion element, they are found in the hemoglobin of the blood. The chlorides, an ion, is present in the stomach. Actually, your stomach and mine, they are generally acidic with the potential of hydrogen, what we call pH, between 1.5 to 3.5. During starvation, it's usually higher. It can go up to pH of 4 during starvation, but just moments after you've eaten, it goes back down. I'll remind you that the lower the pH, the higher the acidity. The lower the pH, the higher the acidity. The lower the pH, the higher the acidity. So our stomachs are inside our stomachs, we are acidic. The acid present in our stomach usually is HCl that can ionize to give you H plus and Cl minus. So our stomachs are acidic. For magnesium ions, it's needed for nerve transmission and muscle control. We usually call these cofactors that help biological events to happen. In summary, Sodium, potassium, calcium, magnesium, ions, Fe ions, and chloride are common ions present throughout the organs of the human body, which is why it's important to learn this. And someone who is going to teach you anatomy, okay, or physiology will emphasize on this chemistry, which is why some of you need to take this class.